All right, everyone. In this video, we are going to look at another integration technique. This technique is called the technique of partial fractions. And so we will use this strategy, this partial fraction strategy, to integrate specifically when we're looking at rational functions, and specifically when substitution, so the method of substitution or U substitution, fails. So first, just as a reminder, a rational function, what do I mean by that? Well, a rational function is a function that looks like a fraction, right? The word rational meaning like ratio, meaning fraction. And so a rational function is really a ratio of fraction. I'm sorry, a rational function is a ratio of functions, so a fraction of functions, and specifically both of the functions, so the one in the numerator and the one in the denominator, are going to be polynomials. So we could write this, if we wanted, as a p of x, so some polynomial p of x divided by some other polynomial q of x. And so there are many examples of rational functions. Just to list three of them right here. We could have a function like x squared plus 1 divided by 2x, right? So again, that numerator, x squared plus 1, is a polynomial. The denominator, 2x, is also a polynomial, so this is a rational function. Another example, we could end up with x cubed plus 3x minus 7 divided by 17, x squared, also a rational function. And one more example, we could have something like 1 divided by x squared minus 1. Here, the denominator, x squared minus 1, is a polynomial. And the numerator, just a constant number 1, is also technically a polynomial. We're thinking of it here as a degree 0 polynomial. So all three of these are examples of rational functions. But both pieces, the numerator and denominator, need to be a polynomial. So if I had something like the square root of x divided by x plus 1, this is not a rational function because that numerator, the square root of x, is not a polynomial. So we are going to use the method of partial fractions specifically to try to integrate rational functions, so polynomial divided by polynomial. And we'll specifically do this in circumstances where substitution or a more elementary technique fail to work. So looking at a couple of examples really quickly, I should say a couple of non-examples, because in all three of these examples, method other than partial fractions will work, right? So classic substitution, for example. Our non-examples, we have these three, and let's quickly run through them. The integral of 1 over x dx. This does not really require any technique. It just requires us to remember that 1 over x has an antiderivative that is the ln of absolute x plus c. Right, so 1 over x, its antiderivative is ln of x. Completely done, no further method necessary. For something like 1 over x minus 1, this is a little bit trickier because it's not just an x, it's an x minus 1. But what we're going to do in this case is use our method of substitution. And so let me come over here to the side and in my scratch paper. Specifically in this case, because the denominator is an x minus 1 and the numerator is the derivative of x minus 1, we can use substitution. We can let u equal x minus 1, and that just means that du will equal the derivative of x minus 1, which is just 1 dx. And so we just get du is equal to dx, and this integral transforms into another integral, which is 1 over u du. And now this integral is exactly the same as the one right above it. We're just looking for an antiderivative of 1 over u. So we get ln of u plus c And then to put a bow around it, we should sub back in. So we get the ln of x minus 1 plus c. Okay, so this one was a little bit trickier, but we could do it just with substitution, and specifically recognizing that the numerator was a degree 0 polynomial, the denominator was a degree 1 polynomial, and specifically, they lined up in such a way so that the denominator as a whole could be the expression u as part of our integration. This last example has a degree 1 polynomial divided by a degree 2 polynomial, so 2x divided by x squared minus 1. But again, it is lined up in such a way that the denominator could be thought of as a u, and the derivative of that is present in the numerator. So here, sort of doing the same scratch work idea off on the side, we could let u equal x squared minus 1. We could let du be the derivative of that, so that's a 2x minus 0 dx. And so with the 2x dx substituting in for the du, so this piece here substituting in for the du, this whole thing becomes the integral, again, of 1 over u, so that u is in the denominator, and then the 2x dx becomes our du. And now our integration is exactly the same. The antiderivative of 1 over u is the ln of absolute value u. And again, we can end by substituting back in. We have ln of u, which is really ln of x squared minus 1 plus c. So a very similar process to the problem above it. Okay, so these three examples were all examples that we could approach using our classic methods, either by recognizing the recognizing the antiderivative of 1 over x, or performing a u substitution. Now, partial fractions will be a technique we develop for integrating when substitution fails. So let's take a look at an example where substitution does not work and see what we can do. So the example that we're going to do is the antiderivative of 1 over x squared minus 1. And our goal is to try to figure out how to approach this. Now notice we cannot use the method of substitution, the method of u substitution, because if I tried to let u equal x squared minus 1, so that same piece in the denominator, the du would need to be 2x dx. We have our dx, but we don't have a du. And so we have our dx, but we don't have a 2x. And so we cannot fully substitute in and get a du as an answer. So we cannot actually complete this substitution. So we will not be able to do that. Instead, we'll learn this new technique, the method of partial fractions. And partial fractions will rely on factoring. So our goal is going to be, so let me draw a bigger sort of scratch work area here. Sort of cut off this entire area for our scratch work. Partial fractions will ask us to look at this expression, 1 over x squared minus 1, and to rewrite it using some factoring and some algebra strategies. We can do this because each of the pieces, the numerator and the denominator, are polynomials. And so we have our, sort of our factoring and our other algebraic strategies that work on polynomials will work in this case. Specifically, we're going to try to factor the denominator here. So in this example, we're going to leave the numerator alone. But the denominator, x squared minus 1, that can be factored into an x plus or minus something times an x plus or minus something. And remember, we want the plus or minus pieces to multiply to give us -1. And then we're also going to want them to add to get 0. There's secretly a plus 0x in here. So worth a review if you're a little rusty on this process, but we end up factoring this denominator into x minus 1 times x plus 1. right? And we can always check that by distributing in the denominator, multiplying this out, foiling, and we will get x squared plus x minus 1. So x squared minus 1. And we've rewritten this after factoring. Now, this is a rational expression, right? So this is a fraction. And I cannot just split this up across the denominator. But what I can do, and what I'm going to try to do, is to rewrite this as some number over x minus 1 plus some other number over x plus 1. So my goal here, right? My goal is to rewrite the rational expression up above as a constant over that first term, the x minus 1, plus another constant over that second term. And we'll need to figure out what a and b are equal to. These will be specific numbers that we'll need. And so we need to find this. Let me fix that parenthesis there. We need to find a and b. But before we go and find those, let me just preview what we're trying to do here. If I can rewrite this expression, the 1 over x squared minus 1, as this rational summation, I could then, jumping back over to my actual work, I could rewrite this original expression as an integral of some number over x minus 1 plus some other number over x plus 1. And then I would have these two individual pieces that I'm trying to integrate. And both of those could be treated in a manner similar to this middle manner here. So notice the 1 over x minus 1, that looks very, very, very similar to what we would end up with down here. For both the a over x minus 1 and then separately, but equivalently, the b over x plus 1. So our goal is to figure out a and b, to rewrite our integral as it appears on the left, and then to integrate each of those pieces using one of the non-example strategies from up above. Okay, so let's give this a go. We can proceed if we figure out what a and b are equal to. And we'll go ahead and keep working in our scratch paper on the right to figure this out. So we have this expression. I'm just going to rewrite this over here. And my goal for the moment is going to be to rewrite this equation by multiplying both sides of the equation by x minus 1 times x plus 1. All right, and so let's confirm what we're doing here. I'm gonna, what do I want to do? Let me get rid of this. And let me lasso and sort of move this out into the middle here. Okay, my goal for the moment is to rewrite this entire equation, multiplying both sides of the equation by x minus 1 times x plus 1. And over here, multiplying this side of the equation by x minus 1 times x plus 1. So in doing this, the left-hand side is definitely just going to be 1, right? Notice we have an x minus 1 times x plus 1 in both the numerator and denominator. So the x minus 1s are going to cancel, the x plus 1s are going to cancel, and we're just left with a 1. What happens on the right-hand side? Well, on the right-hand side, let's focus on the a expression first. The a expression will multiply by the x minus 1. That will cancel with the denominator. And then we'll also multiply by the x plus 1. And so what we're left with there is a times x plus 1. And I encourage you to pause the video and to just confirm that when we multiply the x minus 1 times x plus 1, and we multiply that by this first piece, this piece here, what we get is an a times x plus 1. Okay, the second half is going to be similar, the b over x plus 1. Well, when I multiply that by x plus 1, that will kill the denominator. And then when I multiply it again by x minus 1, I'm going to get b times x minus 1. And so I get this expression here. So this purple equation is equivalent to the green equation in the line above, just without any denominators, right? So I multiplied through by this common denominator to try to eliminate any denominators, and now I just have this purple equation. And so that equation is going to be the equation that we try to solve. I'll see if I can box that. Our goal was to identify A and B. And so I'm trying to find constants A and B that make this equation hold true. And I'll write that down to remember that that's my goal. The goal is to find A and B that make this true. That make this equation true. That make these two sides actually equal to each other. Now, there's a few different strategies for doing this, but what I'm going to introduce in this video is what we call the method of strategic substitution. Specifically, this equation, we want to find values A and B that make this equation true, and we want to make this equation true regardless of our x value. In other words, we want this equation to be true for every single possible value of x. That's what would make these two functions equivalent, or that's what would allow us to rewrite this function, is if these expressions are equal to each other for every single value of x. So to do that, we are going to strategically substitute in and say that if this has to be true for every single x value, has to be true no matter what x value we choose, let's strategically substitute in some x values. And I'm going to say at x equals 1, that's a good value to sub in. We'll see why in just a moment. And at x equals -1, that is also a good value to sub in, and we'll see why here in just a second. So at x equals 1, we get the equation 1 equals a times 1 plus 1 is 2, plus b times 1 minus 1 is 0. And because we strategically substituted in x equals 1, we get this b times 0, and the b term cancels out. This gives us an equivalent equation of 1 equals 2a. And so we get a value for a. We get a equals 1/2. And so to summarize, if the boxed equation holds true for every value of x, it must hold true for x equals 1. And the only way it can hold true for x equals 1 is if this a value was equal to 1/2. So a is equal to 1/2 here. Similarly, if it should hold true for every x value, it should hold true at x equals -1. And at x equals -1, the equation was 1 equals a times, now notice this, -1 plus 1 will make this term 0, plus a b times a -1 minus 1, so a -2. And by strategically substituting in x equals -1, we made this first term cancel out, and we get the expression 1 equals -2b, which means b is equal to -1/2. And again, if the boxed equation is true no matter what, then it must be true. I should say, if it's true no matter what x value we choose, then it should be true at x equals -1, and therefore we would need b to equal a -1/2. So I'll put in the, sorry, that got messy. I'll put in the -1/2 right there. Okay, and we have identified a good choice of A and B. With all of that scratch work done, let's return to the left. And on the left-hand side, we have the integral that we were originally trying to find, the 1 over x squared minus 1. This will equal, I'm just going to rewrite the line above, the a over x minus 1 plus b over x plus 1 dx. But it's no longer a and b. We've found the appropriate choices of a and b. We've said that a has to equal +1/2, and b has to equal a -1/2. And I'll just throw that negative sign out front like this. Okay, and with that, we can proceed. I'm going to rewrite this entire integral. The 1/2, because they're just constants, can be pulled out of the integral sign. So this is 1/2 times the integral, 1 over x minus 1. And then we've also got this -1/2, and we've got an integral of 1 over x plus 1. And so we can compute each of these integrals separately, and each of these are going to be using exactly that starred technique from before, right? And let me scroll up. The starred technique, we just had a 1 in the numerator. We had an x minus 1 in the denominator. The x plus 1 will behave similarly. We can use u substitution for each of these, letting u equal the expression in the denominator. And so what we'll see is that this first piece, the 1 over x minus 1 dx, just like up above, this became the ln of x minus 1. And then we have a -1/2. And if we go and work through the process of substitution on this integral, we will get the ln of absolute value x plus 1 plus c. And this gives us a complete, correct answer to our original integral. So, in summary, this method of partial fractions works by looking at rational expressions that we cannot integrate just by using basic techniques like substitution. The method itself, the real heart of the method, is in our scratch work here on the right. But the idea is that we want to rewrite, and I'll circle this in red, the idea is that we'll want to rewrite our rational expression into a summation of a bunch of simpler rational expressions. So it's that first big idea there, that the 1 over x squared minus 1 can be rewritten. The strategies for rewriting this, a few of those strategies we highlighted here on the right-hand side in that scratch work, but it came down to identifying the appropriate summation of fractions that would algebraically get us back to 1 over x squared minus 1. Once we did that, once we spaced this out and we calculated a good constant a and b, the rest of the integration was relatively simple, coming from the strategies that we discussed at the start of this video. And so this kind of approach can work for many kinds of rational functions, and it gives us an important new technique in our growing list of integration techniques. So that's going to do it for this video. Thanks so much for watching. See you all next time.